I'm still shaking out the apparatus, but let's start with looking at some tones. Okay, here is a 1 kilohertz tone, and you can see there's some distortion in the waveforms, and of course it shows up in the FFT, so there's a fundamental at 1 kilohertz, and then there's a bunch of other harmonics and frequencies in here. So let's try it at a different frequency. This is 100 hertz. So the 100 hertz is pretty ugly. I'm going to have to generate this from the scope because that MP3 player is not doing a very good job. So let's take a look at the transform while we're here. It's good, starting at 0 and stopping, I don't know, minimum. Yeah, there's even more harmonic activity going on in this thing, so I'm going to have to get a better sine wave. So I have the oscilloscope putting out 100 hertz sine wave. So clearly it's the speaker that cannot do this 100 hertz thing. I will try this driver down here at some point to see if it does a better job at low frequency. Obviously this piezo speaker is not very good at low frequency. So I'm going to try a quick sweep and see how that looks. Wow. So I have it sweeping from 100 hertz to 2 kilohertz, and obviously there's a whole pile of stuff going on. The amplitude is not constant at all. Sometimes the microphone goes crazy, sometimes the vibration sensor peaks at different frequencies. So there's a lot of stuff going on. I'm going to have to, nail down the vibration sensor with some adhesive and see if we can't get better results. But a lot of this could be the speaker or the microphone and so on. So it's a good test though. There's a lot going on here that needs to be explained. And just for fun, this one's going from 500 hertz to 5 kilohertz. Not much fun to listen to. Okay, it looks like my audio amplifier was saturating, so I reduced the input amplitude, and looks a lot more like a sine wave. But as you can see, they have the microphone and the vibration sensor are detecting different resonances, where one gets a high amplitude, the other one does not, and vice versa. Okay, you can see this. The spectrum here has a pretty high tone, and the rest of it is 40 dB down, which is pretty good. So it's a lot better when I reduce the amplitude of the signal. And you can see it even looks more like a sine wave up there. Okay, I've set the scope up so that it's outputting to the speaker, and I've put the vibration sensor on with some adhesive, and we're going to sweep the frequency from 10 Hertz to 20 kilohertz and try to get a Bode plot of the frequency response. So I think I'm going to try and start the frequency sweep at the same time as this 10-second trace. And of course it takes 10 seconds. So we have, this is the frequency ranging from 10 Hertz to 20 kilohertz, and this is the amplitude of the waveform. So you can see that at 12 kilohertz we've got peaks, and it's not very high down at the lower frequencies. I'm not sure how much of that response is due to this speaker and how much is due to the vibration sensor, but probably most of it is due to the speaker response curve. And we'll try the same thing with the other driver and see if it has a similar response curve. And let's try it again just to see if it repeats the same pattern. Looks pretty identical to me. Of course, this isn't the ideal way to get a Bode plot, but it's really neat that this scope can actually give you some kind of a Bode plot just by sweeping the frequency and having the time base about 10 seconds and just capturing all those samples. Incidentally, it is capturing samples at 83 kilohertz. Okay, I've set my scope up to have a rolling plot with about 1 second per division, and it's going to capture a sweep of frequencies from 10 Hertz to 20 kilohertz in 10 seconds. Now there's 12 divisions, so we'll capture a bit more than one sweep. So if I started running, it's in the middle of a sweep here, and that marker is the start of the sweep at 10 Hertz. And you can see this speaker has a pretty low response at the beginning, and then it peaks out here. And then that's the start of a second sweep. So I'm going to stop the display when we get a full 10 seconds on the screen. There we go. So between here and here we have 20 kilohertz. So each division is about 2 kilohertz. And that's the frequency response of this speaker, which is kind of all over the map. The vibration sensor has a fairly flat response throughout this whole frequency range. So this is showing that this piezoelectric speaker has a fairly odd frequency response. So I just put the speaker box on top of the sensor, or on top of the speaker, just to see if it changes the frequency response at all. And perhaps it's a little better at the low end there. I'll take a look more closely when we stop it here. So I'll be able to compare this with the previous run. But these sweeps are very consistent in terms of the frequency response. Okay, I have this little driver being driven by the MP3 player, and you'll notice even if I put the microphone right up to it, you probably can't hear anything. But I have mounted the vibration sensor on the bottom of this plastic container, And as soon as I put this on, that driver will start driving the plastic container. It's much louder than the piezoelectric speaker, and it's clearly got better fidelity. So now I'm going to drive it with a sweep function and see if it's got a decent frequency response. Okay, I stuck the vibration sensor directly over the speaker driver, and we'll just see what kind of a plot that comes to. That's the tail end of the high frequency stuff. Here we go, starting at 100 hertz all the way up to 20 kilohertz. And you can see it has a much more frequency response down here. That's 2, 4, 6, 8, 10. Up to 10 kilohertz it has pretty good output, and then it tapers off up towards 20 kilohertz. So this speaker actually sounds a lot better than the other one. And it's still not a hi-fi speaker or anything, but certainly better than the piezoelectric speaker. I'm going to set that down to 10 hertz and just see if we can see any difference there. So we have to go into sweep, and by the way, I'm just using a mouse connected here to enter this stuff. This oscilloscope is great. You don't have to use the touch screen if you don't want to. You can use a mouse, or you can use the control panel. Really flexible. Alright, so that's 10 hertz, and let's get rid of the menu and let her run. So, pretty nice. Let's give it one more trip just to show that it's very consistent between the different sweeps. So there is definitely a peak here at 2 kilohertz. But overall there's a lot higher amplitude down in the low frequencies, so this thing sounds better than the other one.